is sponsored by the Institute for Energy Efficiency and Center for Energy Efficient Materials. For those of you who haven't been here before, it's Wednesday afternoons at 4, normally here. And if you are interested in following the announcements in the seminar series, there's a sign-up sheet back there, or you can follow us through Facebook or Twitter at the Institute. And thanks to those who make the series possible, the industry partners companies, the Directors Council for the Institute, and the DOE UFRC Award that funds the center. Today we're very pleased to have Steve Wallach here, who has quite a long and varied career in many distinguished capacities. He's a recipient of the 2008 IEEE Seymour Cray Award. He was a co-founder of Convex, which is his next company here, which he'll explain. We also, I think, owe him a great debt for being one of the original founders of the PTAC Commission, for which many of us probably received lots of funding through later information technology grants. And I think today's topic is very appropriate for this series. If some of you have seen Luis Barroso speak as part of the Institute's series, one of his topics has also been that we've done really well with, for example, data center infrastructure and delivering power to machines, but we're still working on making software more efficient and higher performance.
Okay, well, thank you. Some of this will be humorous to make a point. Some of the presentation make some of you feel like throwing a brick at me, but c'est la vie. And the reason the title is in the last 30 years, basically, the limiting factor to high-performance computing, by and large, has been software more than hardware. And that's why the title. Even though we should have time left for Q&A, this is interactive. So if someone feels they have to ask a question when I make a point or not make a point, it's okay. So we'll talk about HPC software today, what Convey is doing, and the buzzword is, now we got to go to exascale. We cracked the petascale. Next is, the next 4-minute mile is exascale computing. So, the way this started, and it was interesting because I walked the hall. You'll see why I made that comment momentarily. In the old days, we were told, beware of Greeks bearing gifts. The famous story of Trojan horse. Now, when I did this was 6 months ago, and today, of course, we don't have to worry about the Greeks giving gifts to anyone. Oops. Today, rather than beware of Greeks bearing gifts, it's beware of geeks bearing gifts. And the reason I say that is all the people from these companies really don't care about high-performance computing in the classic sense. I mean, Google is interested certainly in data center, but it's not necessarily taking a single image and making it run 1,000 times faster. And we'll see what the consequence is of that statement. So what problems are we trying to solve? We certainly have new hardware paradigms. Probably the biggest problem is uniprocessor performance is leveling. We hear about the clock speed is basically the same. So that's why we have multi-core computing. So in the past, we were always used to every new generation of chips, the clock cycle would be 20, 30% faster. Now that's not the case. In fact, some would argue it's actually going down. And instead, we're going from 2 cores to 4 cores to 6 cores to 8 cores. So what we're seeing is massive parallel processing and multi-threading we're seeing on a desktop. Even when Intel talks about a chip, or for that matter, Apple, you'll say 2 threads per core, even though 99% of people have no idea what that means. So why do I say deja vu? What's happened in the last 30 years? Multi-core has evolved. We have many-core ILP, which basically means Intel Itanium, fizzled. That is instruction level parallelism. And what we've seen is the x86, whether this be Intel or AMD, has really been extended with extra highly semantic rich instructions, SSE2, 3, 4. Basically trying to find one instruction to replace 10 or 20 instructions. So things like for cryptographic AES, instructions to help you do JPEG encoding. And what we're seeing is basically performance enhancements by archer parallel instructions for acceleration. Now I realize most of you don't know who Yogi Berra was, but he was a catcher, famous catcher in the New York Yankees way back when. And he came up with the statement, it's deja vu all over again. And the reason it's deja vu all over again, because today we're trying to find out how do we get more performance with FPGAs, IBM Cell, GPUs. And the problem with all three of these, it's a different software environment from the standard micro that we have. So what we have is heterogeneous computing again. Heterogeneous in the sense that we have an x86 and we have a coprocessor that's very different than the x86. That's one good definition, or very applicable definition of heterogeneous computing. In terms of languages, we see Fortran evolve. C, of course, has evolved. But I claim we have a bump in the road. How many people here have programmed the GPU with CUDA? So I'm only going to offend 4 people, okay. And let me explain what I mean. The standard high-performance HPC benchmark is matrix multiply. I mean, you can write it many ways, but that's the simplest way. On a vector machine, the code that's generated is very simple. So what happened is, from the Portland group, which has a Fortran to CUDA translator, this is right from this journal. Because the GPU is on an I/O bus, they have to mallocs, they have to do mem copies back and forth because it doesn't share the memory of the host. They have to create threads. And the actual inner loop where you do all the work is this. But you have everything else around it to deal with the fact that it's a different programming environment, it's not virtual memory, etc. And the reason I show this is if you looked at array processors in 1980, like for the FPS, you would see a very similar type of code. So to make my friends at NVIDIA feel good, I developed a term. The term is pornographic programming. You can't define it, but you know it when you see it. And the reason I say this is this is part of HPC, the software, the Trojan horse, is ultimately the machine which is simplest to program will survive. Because user cycles are more important than CPU cycles. It's easier to get money to buy equipment potentially than it is to find 5 more people to write your application. That's the real world. So another way of viewing this was from a presentation approximately a year ago from a former colleague at Los Alamos, Pat McCormick. And the way he expressed what I had on the previous slide was as follows. This is hurdles. You see 3 people basically running to be number 1, and 1 person is hitting every hurdle and obviously will not win. So in Pat's own way of humor, he goes, find the accelerator, they're number 1. Find the programmer hitting the hurdles. And as you can see, you have to completely rethink your algorithms, like in that example of matrix multiply, which is actually a very simple algorithm. Now, instead of that, imagine you have 100,000 lines of code, what you have to do. And tuning is still time consuming. It may compile right away, but it may take you 6 months to actually tune it. And real applications may have 100,000, a million lines of code. You can't do that to real applications. People won't do it. So you have to look at programming models. More and more, yeah, it's always fun doing a Google search when you put, when you're looking for certain pictures, and obviously that's a cute picture. More and more people today are not necessarily looking at writing in high performance languages. They're looking at Java, JavaScript, server-side programming. MATLAB is used extensively. And the major reason MATLAB is being used, among other things, is I can write an application in MATLAB probably in a tenth the time that it would take me in Fortran or C to get it to work. And I was on a MATLAB advisory committee for a while, and it was amazing. The users would come in, sure, it runs 3-4 times slower than if I compiled, but I'm done so fast. And depending on what you're doing, time to develop may be more relevant than, because if it's 3 or 4 times slower, their view is, I'll buy a cluster and it'll run the same speed. I can fix it with money, not with my time. So this is a good example where people are trading off productivity for performance. And that's a $1 billion company, so this is not insignificant. Now, to me, this was the most telling thing. What languages are being used? So I have no idea how this firm got this. But they did an analysis which shows Java, C, etc., and whether it's staying the same, being used less, or being used more, and what percentage. And what was interesting is I was walking the hallway, there was a little notice, tutorial for Objective-C in a certain room. And it shows Objective-C is the language which is growing the fastest. And why is that growing the fastest? Because people want to program this, not program computational fluid dynamics or something else. Well, the people programming this are not interested in high performance computing. They want to get it out as fast as possible and have Apple approve it in the App Store. So this is the top 20. And you can see MATLAB is where its position is. So here's the bottom 20, or bottom 24. And what's interesting here, is here's Fortran. They show COBOL higher use than Fortran. So the question I always ask, how many people have here consider Fortran one of the language they would program an application in? Who are, okay, and I was going to say over 40, under 40. No, the reason that's important is some of my company's biggest customers have 1 million lines of Fortran. Their company is run the numerical side, and there's no way they may change little parts of it, but no one changes 1 million lines of Fortran that works. They may incrementally change it, but not from scratch. But it's irrelevant whether this is first, second, third, or whatever. But this makes sense because the iPhone, and Java makes sense because of the web and Python. And what that means is schools like yourself, the students are more apt to be here than they are here. And that hurts high performance Fortran. I'm sorry, high performance computing, even if it's just programming in C. So then we go to interpretive languages. What a lot of people don't realize is if you go way back when, the first machine I ever programmed was the IBM 7090 in the early 60s. Their assembly language was actually called the FAP, meant Fortran Assembly Program. So they're actually producing a Fortran machine. Then Burroughs, because the compiler writers were always saying, the architects don't know how to design machines. We want to design a machine for us. So they had something called the B1700 with something called an S language, where the compiler writer could create the language they wanted to compile to. They had great compilers, but the performance was terrible, and it was a commercial disaster. So one way of summarizing this is by Kathy Yelich. Kathy Yelich is at UC Berkeley, very well-known compiler person, very, very smart. So when she gave the keynote speech at Salazan, which is a conference held once a year in Oregon on the coast, she, as a compiler writer, was saying, when vector machines were king, parallel languages, this means ignore vector dependency. When you had SIMD machines, in this case the CM5, this was her view. When you had shared memory machines, so every time there was a new architecture, the compiler writers had to do something different. That's the trend here. When clusters, we had MPI. So out of frustration, this is all her stuff. So out of frustration, she goes, we've been at the mercy of our hardware. Will the architects listen now? Now, when I was there, I almost got up and said something, but Don Guerra, Jack that was sitting next to me, knew me, held me down. So the answer is no. And the reason for this frustration is usually there's no what's called co-design. The hardware people do their thing, and the term is you throw it over the wall to the software people. And I'm not going to argue that that's wrong, in my own experience. You try not to do this, to be candid, but for whatever reason, the hardware always seems to come out first, and then a year after that, the software is maybe stable. So let me tell you how we're trying to solve some of that in my new company, Convey. A lot of you ask me, why am I doing yet another company, my third company? I think it's interesting to see how this got started. I was basically sitting in my office doing work for Los Alamos and Department of Defense, and at the same time doing due diligence for venture capitalists. And all these deals would come my way to accelerate an Intel Micro, GPUs, FPGAs, etc. And I would say, oh, you want to build a computer system? Yeah. I go, tell me how Nastran is going to work on your machine. Half the people didn't know what Nastran was, so that was it. Goodbye. It was a simple test. The other half go, oh, that's really difficult to do. And basically, one of them actually got funded but failed. The others never got funded. But the market existed to accelerate the x86 because their major focus, don't worry, it's a very high performance system. But they tend to get their orders more from Redmond, Washington than HPC people, their focus. So one of the people who I'm good friends with happened to be on the board of directors of Xilinx. They had their own project. I reviewed the project and I said, these guys are clueless. They don't know what a computer is. So Xilinx said, okay, we know the market's there. We'll fund you if you can put something together. So I came up with the idea of Convey, went to Intel. I know Justin Ratner quite well. And made a presentation, and he goes, whoa, how do you do that? Where are you going to get the people to do that? And he had a whole bunch of questions. And since I had built about a dozen computers in my life, I could answer it very simply. And he goes, so where are you going to get the people? So as I was telling some people, my response was, I know where they are. My real answer should be where I left them. Because of the first 26 people, 25 worked for me at Convex, and half of them were still employed by HP. So to industrial, Intel, and we're the only computer company Intel ever invested in. And then 3 venture capitalists, or 4 now, I think. So we started a little over 3 years ago. Excuse me. You have one of these here at UCSB. And here's what we did. The key is you program in standard ANSI, C, C++, and Fortran. So there's no equivalent of CUDA or any other language. So half the people in the company are software people. And in fact, the first person I presented this to for an evaluation, I was talking to Dave Austin, we know each other from Rice, was Ken Kennedy. Called him up, very good friends. I said, Ken, I got an idea. I need to bounce it off you. Went down to Rice, Dallas to Houston, you just get on a plane and go. Spent 4 hours, and he goes, whoa, this is really interesting, but you're going to need a real crack compiler team to do this. And I smiled. He goes, oh, I think I know what that means. And off we went. But the key is, and I'll show you why this is now getting a lot of headway. It is program standards C, C++. It leverages x86 ecosystem. And the key is, it's a coprocessor because it extends the instruction set of the x86. So we have all the correct licenses from Intel. You know, part of their investment was all that. So therefore, there's no issue. If you ever build something that sort of looks like an Intel box, Intel's, you know, they have 2,000, 10,000 patents, and you know, they think one of them is going to work, but that's obviously not the case because they're an investor. So what do we do? First of all, we buy a standard Intel motherboard, and we have a mezzanine board, front side bus, FSB, that hooks to a coprocessor. So this is 1U hooked together. And the way this looks like from a block diagram is as follows. Intel chipset, our coprocessor with its own local memory. And the key is it's cache coherent and shares the virtual and physical memory of the Intel processor and the coprocessor. This is very, very, very important. So unlike a GPU, which is not cache coherent, and a GPU is not virtual, so all that code you saw for matrix multiply, you generate matrix multiply as if it was a vector processor. And we have compilers that generate vectorization and parallelization, and I'll go into this in more detail. But as important, we built a very high-speed memory system, 80 gigabytes a second. Right now it goes up to 64 gigabytes, which also has more physical memory than GPUs. GPUs tend to be a couple of gigabytes, which is why you have to manage data in many cases. And we did a lot of clever things. Our memory system is 31-way interleaved. That's not a mistake. I'll ask this university, why do you think we have a 31-way interleaved memory system as opposed to a power 2? Anyone care to speculate? I'm sorry? Yeah. The answer was stride collisions. Every machine I ever did, I always had a program, FFT and things like that. FFT is a power 2. I don't care whether you're a $10,000 computer or a $10 million computer. Computers like Unity stride, so you don't have collisions, as Professor Chang said. So actually in the early 80s, the Burroughs BSP had a 17-way interleave to give credit where credit's due. And the reason they did it is so you don't have collisions. When people write code for a 3D matrix, you tend to see 256 by 256 by 256. You don't see 83. You always tend to see power as a 2. So that was a way to avoid that. This crossbar here is like a router. So now I was talking to you about McKeon. Everything we learned from Chiaro to build a router, we put into our memory switch to be non-blocking virtual output queuing, so we get more effective bandwidth. So from our router days, we understood that when you do something like this, you have to do those types of attributes. And unlike some other people who used FPGAs, and we'll get into some more detail, we have 4 FPGAs which can share a non-blocking crossbar. There's a host interface, and we can now also do scalar processing independent of application specific. So what are some of the benchmarks? Because this is a 31-way interleave, a standard benchmark is basically the equivalent of streams going to memory. So you look at this relative to stride. Well, it turns out on any, I don't care, even the latest Intel Micro, you get very good bandwidth when the stride is 1. When the stride gets greater than 1, bigger strides, the bandwidth goes way down because you're missing cache on every reference. So for certain applications, which are cache busters, performance goes way down. Another way of looking at it is this is the actual benchmark. And this is very typical of a cache-based machine for stride. And these little dips here is when it is actually a stride of 30, 31, or 62. Okay. We create personality. So unlike other FPGA systems where every application has their own personality, own unique bit file, we actually predefine multiple instruction sets. And the key word is predefined statically. So if it's predefined statically, the compiler can have a code generator to generate these instructions. So one of the personality is single precision vector, and this looks like a classical vector machine, multiple function pipes. For our first customer down in San Diego, which has a proteomics, we actually built a custom finite state machine to do match proteins from a database, very high speed. And the compiler generates the instructions to do that. So, and I'll go into this in detail. We do run standard Linux kernel. And when Linux first came out, they didn't support large pages, which you want large pages so you don't take page faults. So we modified approximately 6 kernels. But basically, this is Red Hat Linux, and when you change the kernels, you can't call it Red Hat anymore, so it's rebranded. This is what's actually the most significant from an interesting computer science application. Totally concurrently, at Berkeley, they concluded, people used to ask me, how many different personalities do you need for applications? I would say, hold up my hand and say about a handful. And quite independently, Berkeley, here's the URL. And you can see, here's the structure or the application, if it's HPC or is it database. But in any case, they said there's about 13 things that encompass the application in a technical marketplace. So I took this and said, well, they almost got it right in that it's not 2D, it's 3D, because for each of those applications, you may need a different memory system for optimum performance. So for a structured grid, a cache-based system works quite well. But if I have a sparse matrix, I want a system with a lot of strides that's physical because it busts the cache. So what we're seeing is this notions of application-specific architecture, just like the instructions were application-specific. That's already happening. I believe you also want the memory system to have that notion. And at some point, the compiler complexity as you get to threads and full custom becomes more complex also. So unlike other companies, this was all done at the same time. So we truly did do the code design. So again, how do we create the architectures to do this? Here's what we do. we start off with the base level x86 64, which means we don't have all these artifacts of when it was 32-bit address extensions, all these other funky things. And we add a separate coprocessor for data mining, tree traversal, bit logical, bioinformatics. This is to run things like BLAST, Smith, Waterman. Finance, Black-Scholes, vector finite element, and I'll go into this one in more detail. We haven't done this. I just put this as a placeholder. That if MATLAB runs 4 times slower because it's interpretive, let me build a MATLAB machine. Vector signal image processing, etc. And the reason I show this is each one of these is mutually exclusive. That is, you have this or you have this, but exclusive only at execution time. If you go in from this application to this, the operating system will automatically reload the FPGAs. The user doesn't have to worry about it. It's like demand paging. So here's our compiler. We started off with Open64. You download it, and now we're making substantive mods. We've totally rewritten, and this is almost complete, the vectorizer code generator. But unlike other compilers, its .O's is compatible with GCC and the Intel 64 compiler, Linux compiler. So if you have 1,000 .O's and you only want to recompile to use the coprocessor, 20 of them, you keep 980 from the GCC and 20 from the Convay compiler. So the way this works is you take C, C++, Fortran, and the compiler knows which personality, and it generates both x86 and coprocessor instructions. So it's one compiler if you want. Where if you have CUDA, for example, you have to have an Intel compiler generating Intel code and a CUDA compiler generating graphics code with calls in between. And one of the things we're now doing is 3D finite difference. And the reason I show this is I go to all these workshops in high performance computing. Everyone says, we're doing vector processing. You hear that all the time. But if you ask them, what are you really doing? They're dealing with matrices. No one deals with vectors. If I'm doing hydrodynamics or fluid dynamics, I have a 3D structure of something and I'm solving it. But the reason they're using the term vector processing, because when it started with the Cray one, it was a vector machine. There was not enough physical memory to do a matrix. Well, today, the whole matrix fits in memory, and we're actually defining matrix primitives that say add one matrix to another. So this is what it looks like. And usually what you have to do is you have a 3D matrix, and you take points, a stencil is the term, and that's how we work on it. So that's another view. Okay. And this is internally, this is the architecture. Now this is on an FPGA, 4 FPGAs. If your next application is running Smith Waterman, you overlay it with the Smith Waterman personality. So that's, as I call it, the pedal graph. And the reason a lot of people find this interesting is one instruction or a sequence of instructions may replace a whole loop otherwise, and it reduces less power. If I do one code versus 10 codes, I'm using 1/10 the amount of power for D code. And because this has no cache, if you have a cache and the stride's not 1, I may be only using half the number of operands that I load. If you have a vector machine that says load 83 elements with a stride of 3, you only load those operands. There's nothing loaded on either side. So there's a benefit even in power consumption, or for power consumption. So now we get to Exascale Computing. This was December 2010. I mean, there's a lot of slides, but this is the slide that scares everyone. Why? Because they're saying they get an exascale system by the end of the year, you're going to need 1 billion threads. That's what the B means there. When they put this up, the compiler writers almost fell on the floor because they said, there's absolutely no way we know how to do that. We don't even know how to approach it. 10x the memory bandwidth. Basically, they put this up and said, please give us $1 billion a year for the next 5 or 6 years to figure this out. And the other major thing is, how do you hook all these things together? The nodes. We'll put this, how do you enable all these billion threads to work together? No one knows. The only thing that the consensus is we're going to need optical networking because we need the bandwidth to do it and it will be less power. But other than that, they don't know. So some of the conclusions, again, the number of cores will double every year. We may have 1 million processor machine by 2015. How do you program 1 million processors? It truly is unknown. And even the keynote, performance will become a software problem. So realistically, you may get more performance by compiler optimizations than Moore's law. Which is an interesting comment, because if I said that 20 years ago, I'd be laughed off the stage. You know, it would be, you're crazy. Because everyone saw that every generation things got faster and faster. Now they're not, and if anything, they're becoming more complicated because it's 1 million processors. So just lastly, okay, I believe uniprocessor performance has to be increased. We can't just say it's level. And the way Convey is approaching it is this application specific. That is, rather than just taking any machine and programming matrix multiply or whatever, a Linpack machine, let's build a personality which is tuned to one of those dwarfs or motifs. Because we may get 2 or 3 times the efficiency over and above a general purpose machine. And I honestly believe that. Again, certainly heterogeneous computing is here to stay. I think everyone agrees to that. Again, easiest to program will be the correct technology. So even for GPUs, a lot of people say OpenCL is preferred over CUDA because OpenCL is a standard where CUDA is a very vendor specific. To make life more difficult, we're going to see smarter memory systems, the term PIM, processor and memory. That's going to really complicate things. And the reason you'll have that is because the memory wall, as people say, that the latency to memory is so much greater than the clock cycle that we have to make the memory smarter. Of course, new HPC software must be developed. Again, I keep coming back to smarter compilers. I believe what's on the last statement was correct, that software will make the machines run faster, not slower. But I believe it has to be architecturally transparent. We can't have machines with different architectures requiring total recoding of the application. There's not enough people in the world to do that. And we need new algorithms, not new languages. The reason I'm saying all this, when Convex, my previous company, whenever we had difficulties, oh, the compiler can't do this. And I'm not saying it because we would go to guys like Ken Kennedy who would go, oh, that's an interesting problem. I never thought about that one. Give me 2 weeks to see if I can come up with an answer. And 9 times out of 10, he and other people at Rice came up with how to do it automatically. So rather than saying, let's put that feature in a language, we took the tack, let's see if we can do it automatically. And I think that's a very important lesson. So lastly, we always have to end with Dilbert, who of course is the smartest computer person in the world. And it's the only cartoon I read every day. As a lead software engineer, I give you the first unit of our 10,000 copy production run. Wow, I wish we designed it with the features listed on the box. That would have been awesome. I'll put this with the other reminders of how my life could have been excellent. Thank you. So please, seriously, feel free to ask any question on anything. Yes? I'm sorry? So the question is, how do you profile applicate with GDB? You profile applications as standard Unix. You compile and you get a listing of which subroutines.
Yeah, but then you must do some sort of classification you must classify them, the profiles in order to come up with these personalities.
No, we don't do that. The lady said, oh, once we get the profile, then we figure out the applications. Okay. In the general case, if you're just compiling standard Fortran or C, it's no different than, look at, reprogram it this way, whatever. When you're doing something that's a very custom, like bioinformatics, like Smith-Waterman or BLAST, we're going through this now. We spend a lot of time just profiling it in C, and what you hope, and I have to emphasize the word hope, is 1 or 2 routines is 95% of the runtime. And if that's the case, you then look at those 2 routines and you create FPGA, a FPGA version. And generally in high performance Fortran, you tend to see that, 1 or 2 routines is high percentage. If that's not the case, I wish it was, then, and we're doing this now, I won't tell you which application. We have modified the application, but this is Amdau's law. You have something that's 95% of the runtime. Wow, I can make this now go 100 times faster, so we call it the speed of light. So what was 95% takes it down to 0. So now what was left, the 5%, which you never care about, is 95% of the runtime. It's just the opposite. And you get all these little routines that are junk, that no one ever worried about tuning because it was an insignificant aspect of the execution profile. Now that you took everything else and made it run so fast, these, what are, let's say, what you believe were statistically insignificant, become significant. So it's an iterative process. And because x86 is part of the execution, in some cases we will take that 5%, I'm telling you in reality, and just tune it in C or make it multi-threaded, because usually it's not multi-threaded, and we actually use the multi-core of the host x86, because they can run at the same time, the coprocessor, and take the 5% down to 2%. That's actually an excellent question, because sometimes it's easy, sometimes it's not. A general development of a personality from beginning to end is 4 to 6 months. This is with our people write it, don't use C to Verilog. They actually code it in an RTL directly, so we get approximately a 2x increase in performance. That's the clock cycle and density. In fact, probably the best thing that can happen to programming FPGAs is all the tools which exist, become as efficient as writing, directly in the RTL. I believe that'll happen, but it may be 10 years away. It's an excellent question. Any other questions? The question is, how do these personalities get created? Well, first of all, in general, we write them, but we have users. We have a PDK development kit that people can write it. And if they used the Convey PDK, there's already stubs, like you don't have to worry about interfacing to memory or interfacing to the coprocessor. And if you want to write it in C and use a C to Verilog translator, fine. The ones we write, it's just a catalog item. They're shipped. So if you compile and say use the single precision personality, when it executes, the operating system, if it's not already preloaded, will load it in. You can reuse it. If you go from one single precision to another, let's say, you just reuse it. And we have a full library of BLAS, LAPAC, et cetera. It's a real computer. See, the reason I say that is a lot of the world, to be candid, was jaded with people who had FPGA systems like DRC, SRC, B, which is really just a group, I don't mean to knock it, a bunch of FPGAs on a board going to memory where the user was left to do everything. It didn't have virtual memory, and, so you had to manage your memory, you had to manage the communications back to a host, and that takes a lot of time.
Any comments or thoughts? Just, I mean, one of the issues, of course, is we're just bumping up into the physics of silicon, like you do with it. What about, I mean, we've been hearing about it forever, but some of these other materials.
Okay, the question is that we're bumping up to the limits of silicon. I'm a DE. And all I know is every time I've ever heard there was a limit, it just seems to I don't know how to do it, but it used to be you can't go below 1,000 nanometers, 100 nanometers. Then you couldn't go below 50 nanometers. Now, sure you can do it, but all of a sudden the fab went from $250 million to $4 billion. Do it. And I only know what I read, like IEEE magazines and everything. They're saying, like these people just got the Nobel Prize. Maybe graphene, in 10 years will be the base level material. The only thing I think that'll happen, I was mentioned earlier, is you'll see optics eventually go, I believe, chip to chip. Because you need bandwidth, and optics is much more efficient from a bandwidth perspective. Not optical computing. I want to make sure but every time everyone's ever said, that question comes up, I go, I'm a double E, just tell me how to design with it, and I'll figure out how to do a good job. But it's clear the entry is measured in billions. One of the reasons there's a consolidation, you may not have thought it this way. 15 years ago, there were, pick a number, 7 people with microprocessors. DEC had Alpha, there was MIPS, there was Spark, x86, Motorola, IBM. One of the major reasons this all got consolidated is because it's now it's $5 billion of fab. The major cost is depreciation. Whether someone's in there or not, once you turn it on, you depreciate the equipment. 70% of the cost is equipment. This is what I've been told. Depreciated over 3 years. Whether it runs 1 hour a day or 24 hours a day. And if you don't have a volume of 100 million or so a year, you can't be in the microprocessor, which is why you have companies like TSMC, for example, in Taiwan, that people have to go to a foundry as opposed to having their own. Well, Intel's big enough. Even AMD is not big enough anymore. They had to sell some of it off. And IBM, you know why IBM produces the Sony, the cell? Is because their volume wasn't big enough on the IBM Power PC, but still want to have their own fab, so they became a foundry. It's not because they wanted to. I shouldn't say that. I don't know what IBM wanted or not, but they needed the volume of the PlayStation to compensate for the fact that they didn't have 100 million parts a year for the Power series. It literally is as simple as that.
Along those lines, Steve, if you've got an Exascale computer with something like 1 million cores, that's what you said, I think, what about the reliability issue? I mean, some of these are going to fail.
Yeah, well, there's 2 answers. One is if the MTBF, mean time between failure, is 1 hour, your application better finish in less than 1 hour. So that's the tongue-in-cheek answer. That's probably the real answer. But no, but that's a fair question.
How hard is it to build that into the software?
Well, people don't know how to. The software is not necessarily reliable the way it's currently written, let alone and build it robust. And that's literally a major computer science research effort. But you know, one of them, it's now public. What I'm going to tell you, I mean, public. If you know where to look, you can. You know, these days you give a Google search query to prove it's public. Is at Los Alamos. Now, Los Alamos is 7,000 feet up, so you know the gamma rays or whatever is that much more than at ground level. And by accident, they happened to run this application 3 times, and one of the 3 times they got a different answer. Well, needless to say, they were very disturbed. So as they began investigating, they found out that on the alpha cache tag store, there was no parity bit to show you how far it goes. And the gamma ray or whatever it was causing an upset, you know, and they were getting the wrong answer. And as the geometries get smaller and smaller, radiation upsets actually, which means if you're flying on a plane, if there's 1 million laptops on a plane, you could probably assume there's a fair number of them that are getting the wrong results or rebooting, and it's not Microsoft's fault, it's the fact of gamma rays. But I honestly, I don't know the answer. People are beginning to say more and more that they're going to have to try to figure it out for exactly the reason you posed, is that the calculated MTBF of a 1 million processor system may be such that it doesn't stay up long enough to run an application that could take a month. You know, some of the big HPC applications, even though you have a petaflop, will take a month to run. I mean, there's a reason why they want it. It's not because they want something that runs in 1 day to run in 10 seconds. It's something that could take 3 years to run in 3 months. I mean, that, for those who may not realize, that's the motivation for this. So they don't know. The only thing I've seen that even comes close is they tried to checkpoint restart, do some sanity checks, you know, in the sense where a compiler can't sanity check because you have to know at a certain point, you know, that it's converging or the number or this set of numbers should be less than 1 or something like that. They certainly want the interconnect when you communicate back and forth not to be specific to, let's say, 1 million cores, because if all of a sudden you lose 2 cores and you have 999,998, you want your application to still run with that number. So they kind of figured out. You know, I mean, that's the right answer, right? That is, if you lose 1 core out of 1 million, you don't want to stop the application. So I think the focus is, how do I parallel program, you know, to work in that particular scenario, which is not something they've ever done before, by the way, at least in the most general case. Okay, I think we have time for one more. If not, yes?
The first one is, how did you make the cache coherence between the FPGA and the coprocessor?
So the question is, how do we do the cache coherency? One, we have a license from Intel. I have. We have the full specs, and the people who designed this computer all came with me from Convex, where we've done a half a dozen cache coherent machines, so no one had to be taught what a messy protocol was or a Snoopy protocol. But more important, we had this is Intel. Even though they invest in us, we had to pay for an Intel engineer to be on the other end of an 800 number, effectively. So we could call him up and say, we got this unusual condition. Can you please explain it to us? And he or she would go off, in some cases, run the simulator to go, oh, this is what you have to do. Or, this is real world now. You can get the spec for the Intel memory controller, and there's 300 control registers, CSR for those who ever got into it. And unless you have someone helping you, because the documentation doesn't tell you this, you may have to know, oh, you have to set bit 2 of CSR 10 and then set bit 15 of CSR 25 in that sequence, and it'll work. And if you don't do it in that way, you won't get it to work. And in your BIOS, you got to do it that way. So if you don't have access to that, no way. So that's part A. What's part B?
Actually, yeah, my question was about the latency between both and is it fast enough or I mean the latency of the cache coherence?
The cache coherency is actually pretty fast. The question about latency is pretty fast because that's the thing that Intel tunes a lot, the cache coherency. Because when they have their own processors doing snooping, they want that to be as minimal as possible. So it's measured in, like 100 nanoseconds or something. But it sounds like you've been computer design in your life, but it is not to do the cache coherency. In fact, when we announced it, these people who were making these PCI boards with FPGAs, there's maybe half a dozen companies that do that. They go, how'd you do that? We explain. They go, Intel helped you. I said, they're an investor in us. And they knew that that having the cache coherency benefits the programming model. Remember that example with CUDA, with the moving it? It goes away. It's not a question of simplifying it. It eliminates half the shared virtual memory and cache coherency eliminates half the code that you saw on that example of CUDA. And it's a computer. That's the key. It's a coprocessor. And the reason we use the term coprocessor, way back when, if you want the floating point on the Intel 386, you had a separate chip called the Intel 387. So you do a Google 8387, they say a coprocessor chip to the 386. And in fact, when we presented it to the two people in Intel, one was Ratner, another one was a senior VP. When we showed him, he goes, "Oh, I know that. I was involved with the integration of the 83, 86, 387 way back when I was a real engineer. So I know exactly what you're saying. That's cool. And we have to help you figure that out because a lot of that stuff is buried in all these manuals and stuff like that. But that's the real world." Okay, what last question?
So you talked about optics a couple of times. So it sounds like it was primarily just point-to-point interconnects between groups of processors.
Initially, yes.
So yeah, what is the next? Is there more interesting in terms of some sort of
Okay. So this is a. I'm not sure if it's a trick question or what. Question about optics going forward. Let me see. Hold on for a second. Now, don't look at the screen. Let's see if I have it. I think I have it here. Let's see. I'm looking for my supercomputer keynote speech, if I have it here. No, okay. Yeah, maybe this is it. Hold on. I was the keynote speaker at Supercomputer 2000. So in 2000, what I said is, now remember, this is a petaflop, so you gotta, stage it, but I don't care. One of the beauties of, if you make this an exaflop, just multiply do the scaling by 1,000. So in 2000, I said each of these things is going to be a multi-die multiprocessor. That's another way of saying multi-core. And so I got that right. I said all the I/O is going to be centralized. That's the way the supercomputers, they have these big switches and they run, Panasys or something as common I/O. And the reason I said all optical switch is to get the bandwidth, I don't know how to do it electrically. So what I would prefer is, let me go backwards a little bit. If I had my choice, this is the way I would build things. One way, I'm burying myself, this is public, so I said, is I'll have all these RISC cores. SIA said we can go to 6 gigahertz. They were wrong. It's 3 gigahertz. I have a crossbar. And coming out of the crossbar, I want, WDM directly. And I want to have a flat memory. And if I do that, but if I come out optically here, I want to go to an optical switch. Otherwise, I have latency converting from optics to electronics. And adding latency is always bad.
This is one of those boxes on the previous slide.
Yeah. So, if someone gave me $20, $30 million, I'm not sure I'd do it, but that's one. This has to be done by Intel or whomever. They have to produce a chip where the output from memory, not as an I/O bus, that's the key. And multi-lambda, for those who don't know, lambda is frequency. Electrical engineer, you think of gigabits per second. The optics people think of nanometers of lambda. That's another disconnect between these two worlds. I mean, disconnect. It's just, they're equivalent, but an engineer doesn't think of lambda, they think of bits per second. Okay. And if you can do that, if someone committed to a commercial product with a chip doing that, we'll figure out a way to make the switch do it, is what I'm saying. So literally 10 years ago, this is what I said I'd like to see. Now today, to do the petaflop system, the optics is more in the InfiniBand over optics or Ethernet over optics. But obviously the switch is not optical. And the reason for that is you want the optics because I can do well, we had this discussion over lunch, but in a single fiber, I can have terabits, where if I want terabits electrically, there's no, basically, I have a bundle. I don't have a fiber. Then you talk about bit error rates and stuff like that. It would even be worse with optics because I'd have more drivers and receivers, and MTBF is a function of hardware. Okay. Thank you. So this is yours.